So what if I told you that a mathematical problem, one that has stumped the greatest minds for centuries, might have just been cracked? Today, we're not just crunching numbers. We're going to go on a quest to solve the unsolvable. And the answer, well, it could change how we approach some of the toughest challenges out there in science and technology.
You know, for generations, this is the exact kind of thing that has kept mathematicians up at night. The challenge isn't about getting a close guess. It's about finding the exact answer, the one perfect solution. And for a long, long time, for a certain type of problem, that was considered impossible.
And this is our beast, a 20th-degree polynomial. So what that really means is we're on the hunt for 20 different numbers, or roots, that when you plug them into this monster of an equation, make the whole thing equal 0. Seriously, finding just one is a huge task, let alone finding all 20 of them perfect.
But don't you worry, we're going to break it all down. First, we'll get to know our unsolvable equation. Then, we'll dig into why the old tools just weren't up to the job. After that, we'll introduce the revolutionary theorem that changes the whole game. We'll decode the method behind it, reveal the exact solution, and finally, we'll talk about why this breakthrough is about so much more than just one tricky math problem.
Okay, let's start our climb. This polynomial isn't just some exercise from a textbook. I want you to think of it as a mathematical Everest, a challenge so immense that for centuries, finding an exact solution was believed to be flat-out impossible. So why was this thing our Everest? I mean, why couldn't we just chuck it into a supercomputer and get the perfect answer ages ago? Well, the reason is all about the fundamental limits of the mathematical tools we had.
And this really gets to the heart of the problem, right? On one hand, you've got what's called numerical approximation. Think of it like a blurry photo. It gets you close to the real thing, but it's always a little fuzzy, full of tiny rounding errors. But on the other hand, you have a symbolic solution. Now that is the original, crystal clear photograph. The exact answer, absolutely precise and perfect. For centuries, that was the holy grail for problems like this.
And yeah, there was a huge roadblock, a mathematical law really. Abel's impossibility theorem, which is a cornerstone of modern algebra, basically proved that for many high-degree equations like ours, finding that perfect symbolic solution was literally impossible using the traditional methods. You know, things like square roots or cube roots. For a long, long time, that was it. The final word on the subject. Case closed.
Right. But what if that final word, well, wasn't so final after all? This is where our story takes a really sharp turn, with a new theorem that claims it can do what was once thought to be impossible. And this is where Ezouidi's theorem steps onto the stage. This new method promises to find the exact symbolic roots of these incredibly complex polynomials, and it does it through a structured, step-by-step process. The key idea here is that it's designed to completely bypass the very limitations that Abel's theorem laid down. Okay, so how does this thing actually work? Now, we're not going to get lost in the mathematical weeds here, I promise, but we are going to get a feel for the really elegant logic that's driving this entire solution.
You know, at the very heart of it all is this really powerful recursive formula. I want you to think of it like a recipe from some ancient, brilliant cookbook. You take a few key ingredients, you follow a very precise set of steps, and it builds the solution for you piece by piece.
So let's break down that recipe. First up, you've got these things called binomial coefficients. They're like little dials that fine-tune everything at each stage. Second, there's a base coefficient, which is basically our starting point. And third, and this is where the real magic happens, we have recursive terms. The formula literally uses the answers from the previous steps to build the next part of the solution. It's just a beautiful chain reaction.
So the big takeaway here is that the solution isn't some flash of genius that happens all at once. Nope, it's built systematically, almost like it's on an assembly line. The theorem calculates one piece of the puzzle, then uses that piece to find the next, and then the next, all in this predictable and structured way.
So the process kicks off. It calculates the value for the first degree, where k equals 1. Then it takes that answer, plugs it right back into the formula, and solves for k equals 2. Then k equals 3. And it just keeps going, this loop, step by step, building on itself, climbing that ladder all the way through all 20 degrees of our polynomial.
And after all that, after running through that entire process, what do we get? Well, this is it, the moment of truth, the exact solution. And here they are, the 20 exact roots of that monster polynomial. I mean, just look at how clean and precise these are. 2.0, 1.5, 1.25. These are not messy, rounded-off guesses. According to the theorem, these are the perfect symbolic answers,
the very ones that classical algebra told us were impossible to find.
You know, the source material really says it best. This is not just a numerical approximation. It provides precise, solvable roots for polynomials that would otherwise be deemed unsolvable. It's a direct, powerful challenge to a mathematical belief that's been held for a very long time.
Okay, a super complex math problem got solved. Big deal, right? So what? What's the bigger picture here? I mean, why does this matter outside of a university lecture hall?
Well, this is about so much more than just one equation. This is about forging a new key. The real value of a breakthrough like Ezouidi's theorem isn't just in solving this one problem. It's the potential it opens up as a new tool, a tool that could be applied to a whole class of problems that we used to think were completely out of reach in fields like physics, engineering, and economics.
And that leaves us with one last big thought. This whole thing was a story about questioning the word impossible in math. So what unsolvable problem is out there in your world, whether it's in science and business, maybe even in your own life, that's just waiting for someone to come along with a new way of thinking, a new key to finally unlock it?